he has done his BTech from NERIST, and which is under NEHU. So without further delay, we'll start now, because we have the validity session also today, which we have to wrap up. So thank you, Dr. Mishra, for this session. The session is over to you. You can start, sir.
Yeah. So it's really my privilege to share my research work uh, with you all, and I sincerely pay my gratitude and would like to convey my thanks to Dr. Swanirvar sir, the coordinator and head of the department IT, Tripura University. Let me just give the highlights of previous session, and then I will continue my discussion on the same line. So I welcome you all to this session. So once again, welcome to this session of the event webinar cum FDP on recent trends in electronics and information technology, jointly organized by Department of Information Technology and Electronics and Communication Engineering, Tripura University. My talk is mainly on the phonocardiogram signal analysis, where I will be discussing the most recent works which have been done on the phonocardiogram signal that may assist cardiologists and physician in diagnosis various cardiac diseases. So just let me give the highlights of our previous session. So the talk was started with the brief introduction towards heart sound analysis. We saw the importance of heart sound analysis using signal processing techniques. Then also have we have also seen the state of art, where the first and foremost step in any automated diagnosis system of cardiac diseases is segmentation of first and second heart sounds. And we saw there are various interesting problems related to this research topic in heart sound analysis. And I discussed few works, and today I will continue to continue to share my research on this, but mainly it will be focused on detection of third heart sound signals using variational mode detection. So in the previous talk, mainly we were focused on detection of first and second heart sounds. Today we will be discussing on detection of third heart sound. What are the techniques available to detect third heart sound? And we will finally, what are the major contribution in this area? We will highlight that, followed by conclusion and the future work. So in the previous session we discussed about our phonocardiogram signal. Basically, phonocardiogram signal is the recording of heart sounds caused due to mechanical vibration of the heart, whereas when we talk of electrocardiogram signal, it's a recording of electrical activities of the heart sounds. And these two signals are very much related to each other, and this figure one can relate the relationship between the phonocardiogram signal and electrocardiogram signal. So in phonocardiogram signals we have first sound S1, after that second heart sounds generates. So these S1 and S2 are called loved up sounds also, and termed as fundamental heart sounds. These are the normal heart sounds. It is available to all the healthy persons. But sometimes we hear third heart sound. So this may be very normal in case of a children or in case of athletes. But presence of this third heart sound, it may be a sign of cardiac abnormalities for elderly people or for aged persons. Then we have another abnormal heart sounds, which is S4. It's a very rare heart sounds. uh, and it indicates heart failure. So basically, when we talk of phonocardiogram signals or just heart sounds, it has different components in it, like first heart sound, S1, S2, S3, S4. Some of them are normal heart sounds like S1 and S2. S3 depends on the age, whereas S4 is a rare abnormal heart sound which indicates cardiac abnormalities. Then we have heart murmurs. We have different kinds of murmurs, and from this table we can find that this phonocardiogram signal is a very low frequency signals and low amplitude signals. As a result, its detection becomes very complex in nature, and even the trained physicians and cardiologists, they make mistake while doing auscultation, and sometimes they miss to detect some abnormal sounds also, and even in some cases normal sounds are perceived that they are abnormal. As a result, normal people also they get referred to the cardiac hospitals, which lead to problem to the patients. That's why it's very important to exactly detect the heart sound components for diagnosis using signal processing and machine learnings. So we know that our heart sounds, it contains vital information. It has clinical importance, and any alteration in normal heart sounds, it indicates some cardiac diseases. That's why it's very important to do heart sound analysis using machine learning techniques and signal processing techniques, so that it can it can provide us the tool to assist doctors in diagnosis heart malfunctions accurately. It can prevent the mistakes which occurs because of the need of human expertise and the skill of the physicians. And definitely the reason for segmentation and analysis of these heart sounds is to improve the quality care for the patients. And according to World Health Organization, these cardiovascular diseases are the number one cause of death globally, and the most conventional method is auscultation, which uses stethoscope to know or to hear the heart sounds, but it's quite subjective and depends on the expertise, and it makes mistakes also. That's why, like, as interpretation of these subjects are subjective, so for one person it may be a normal heart sound, for another they may say it's abnormal. That's why there is a need to create a first level of screening of cardiac pathologies using signal processing technique that may assist our medical experts. So these all we have some basic idea of these things. And in the state of art on this heart sound analysis, it says that the first and foremost step of any cardiac screening system is to segment first and second heart sounds. And most of the researchers are following ECG independent method because it doesn't require ECG as reference signals. Only phonocardiogram signal will be sufficient for segmentation and detection of the heart sounds. So mostly people have preferred envelopeograph approach for segmentation of S1 and S2. Then uh, later on, deep neural network approach has been also reported for recognition of fundamental heart sounds S1 and S2 respectively. And then one of the abnormal heart sound, which is S3. So as its amplitude and frequency is low in comparison to the fundamental heart sounds, so mainly time frequency techniques uh, like like STFT, short time Fourier transform, then S transform, ST, then we have Wigner value distribution, then we have SPWVD, that is smoothed pseudo uh, Wigner value distribution, uh, time frequency representation techniques. So these all have been reported in the state of art for detection of third heart sound. So today we will be mainly focused on this. As in our previous session, we discussed one of approach for recognition of S1 and S2, first and second heart sounds. Today we will switch over to the third heart sound detection technique. But before that, some Other works also comes which is required before the exact detection of heart sound, like separation of heart and lung sounds from the breathing signal. So that will also be discussed. And then one of the abnormal heart sound is the murmur sounds. So generally people have used those features which have been quite successful in the speech processing area. As this phonocardiogram signal is also a heart, it's a sound. So they tried like the very successful features of speech processing, like male ancestral features or linear predictive features in classification of heart sounds also. So it was motivated from the success of these features in speech processing. So that they have tried for the phonocardiogram signals also. And for separation of heart and lung sounds from the breathing signal, they have used non-linear decomposition techniques like empirical mode decomposition. So whenever we talk of objectives, so generally there are various objectives when the researcher goes for phonocardiogram signal analysis. So one can go for building automated noise robust framework for identification of fundamental heart sounds. One can Another area may be the separation of heart and lung sounds from the breath signal. The reason is that heart and lung sounds, they show spectral overlap, and directly use of low pass filter or high pass filter cannot be done, as it will eliminate the desired signal from both kind of signals. That's why people need separation of heart and lung sounds using appropriate technique. Then uh, another work may be on detection of third and fourth heart sounds. Then one research areas lead us to detection of pathological heart murmurs, which is the sign of cardiac failures. Then there is a some designing of low cost stethoscope, which will be equivalent to high cost electronic stethoscope for recording of heart sounds. So we have lots of we have few modules where we can see how a researcher uh, can follow the general method for detection of various components of heart sounds, or for classification of abnormal heart sounds, rather detection of any cardiac abnormalities. So yesterday we built some of the basic concepts of tools and techniques required for handling these non-stationary signals like phonocardiogram signal. And then we discussed detection of first and second heart sound using spectral and convex Hall area. So today, seeing the time, we will be mainly focused on the detection of third heart sound. But before that, very shortly, we will see what are the things required, what are the uh, prior steps before directly detecting the third heart sounds. So these we already discussed, so I will just skip these techniques. Like variational mode decomposition, we already know it's a non-linear decomposition technique that decomposes a complex signal into discrete number of sub signals or modes. And this is the mathematical techniques or mathematical concepts required to uh, understand variational mode decomposition and how to represent that modes into its analytical signal form. And we have amplitude and frequency modulated bandwidths, which can be exploited or which can be used as one of the feature for the non-stationary signals. Then we have to, as these phonocardiogram signals are non-linear and non-stationary signal, so in order to detect or to classify different components, we may measure its non-linearity strength. So that can be found, that can be expressed using convex Hull area. So it may also be a very useful or relevant feature in classification of the components of a phonocardiogram signal. And then we discussed one technique which is meant to to identify first and second hertz sounds using spectral and convex features. And we found that these features are more effective in comparison to the earlier reported features used for classification of S1 and S2 hertz sounds. And those features were MFCC's features, male frequency substral coefficients and its derivative feature. So let us see, this is the proposed flow diagram of S1N. So generally, we take the phonocardiogram signal and then we segment either by with the help of physician for training phase or directly with the help of sun and energy. We segment S1 and S2. We decompose it into two sub modes using variational mode decomposition. Then we extract features from the signal and its two different modes, and these features are spectral and analytical features. When we talk of spectral feature, it's the amplitude modulated bandwidth, and in analytical feature we calculate convex hull area, and then these features are represented in the form of a vector, and then it is fed to a classifier. So this is the general flow diagram of classification and of S1 and S2 signals. So this we discussed earlier. So we have online data. So these websites are very much reported in the literature, and they contain very good data. So we have Littman, Michigan, Washington, Murmur Library, and we can record also using electronic stethoscope. So we all discuss this, how this is our waveform plot and spectrogram of S1 and S2 signal. So we have this S1 signal and S2 signal. Here we have S1 and this is S2 signal. So here we have the timing between S1 and S2 is called systolic time period, and the timing between S2 and S1 is called diastolic time period. So actually systolic time period is less as compared to the diastolic time period, and this is one of the important information that is exploited in the detection of first and second hertz sounds. So this we have seen. So we found that when we use this technique, where we use spectral and an analytical feature, it gives better performance in comparison to MFCC and its derivative features. So this was one work. But sometimes what happens that we have used here conventional method. So one work which was also focused in recognition of S1 and S2 using deep learning method. So here we have used staked autoencoder. So this staked autoencoder method, it in place of SBM, we have used staked autoencoder, which is a deep learning technique. And then in place of features, we tried to use some other features. So there we have used a combinatory features. So in combinatory features, we have used different kinds of features, and we combined that, and then it is fed to a deep learning technique. So that was also a very effective method in recognition of S1S. So this is the proposed diagram. So here we have like this is the proposed diagram. Like we first we have a testing data here. So here we have a testing data. So we will do feature extraction. So before feature extraction, first we segment that into S1 and S2 components regions using hertz sound segmentation block. Then we use a combinatory feature, and combinatory feature here we have used different features, and we have combined this like skewness, kurtosis, linear frequency substral coefficient, mean of power spectrum, then mean of inverse MFCC, then LPCC, linear predictive substral coefficient, mean of perceptual linear prediction substral coefficient, then male frequency substral coefficient, and then we append this with its first derivative and second derivative features along with the log of that energy. So we have used these all features and we have combined this. As a result, we say that it's a combinatory feature and its dimensions become 72. It means that it has 72 number of columns in that feature. In that feature. So basically, like what we are doing here for recognition of first and second heart sounds, we are getting lots of different features which has the capability to to extract or to show some of the information contained in the non-stationary signal, and most of these features have been chosen based on their successes in their in speech processing. So as it is also a sound, so we tried to use different kinds of these features, and we made a combinatory feature, and then this feature was fed to staked autoencoder. So staked autoencoder, basically it provide a deep learning approach. So in case of a conventional so it has replaced our conventional classifier of previously used SVM. So here we have used combinatory feature and we have used staked autoencoder. So if we compare this work with that of the previous work, we find that there we have used spectral and analytical feature followed by SVM classifier, and here we have used combinatory feature, which is a actually which is the combination of different features, and in place of a conventional classifier we followed here deep learning approach where we have used staked autoencoder, and all the things remain same. And then we used here one of the tool that is called FIST, that is called feature selection toolbox. So here in order to understand that what is the contribution of these individual features, or which feature is more prominent in, or which feature is more relevant in classifying S1 and S2 signal. So there we have done FIST analysis also, and this is the method. So our method is based on the staked autoencoder. So here actually when we talk of only autoencoder, so this figure 2a, it represents an autoencoder. So basically it's a neural network comprising three completely connected layers, like input layer, then we have a hidden layer and the output layer. But this figure 2b, this shows the block diagram of a staked autoencoder. So basically staked autoencoder is a network integrating together the hidden layer of subsequent encoders. So we have like input, hidden layer 1, hidden layer 2, hidden layer 3, and then we can go for up to n hidden layers, and then will be output. So basically it's a stacked autoencoder is a network integrating together the hidden layers of the subsequent autoencoders. So we have input, output, and inside that we have several hidden layers of autoencoders. And one thing is that to get its good performance, we always require the tuning of the parameters. So we have to tune certain parameters of the staked autoencoder. So it's a hit and trial method. We have to choose we have to choose different values, and we have to optimize, we have to tune this autoencoder. So while tuning, we found that if we keep the number of hidden layers and epochs uh, each to the 30, if we put sparsity ratio and weight regularization as 0.5 and 0.05 respectively, then it gives a very good accuracy. And it has achieved for this employed staked autoencoder, it achieves an average recognition accuracies of around 94.82% and 95.50 based on the combinatory features. Whereas the state of art method, which uses MFCC and its first and second derivative features, it gives only 72.54 and 57.25 for online and recorded signal respectively. So we find that when we use staked autoencoder, it with combinatory feature, it gives better performance in comparison to our MFCCs and its derivative features. So this was one. Then then another work which was extended was recognition of first and second heart sounds using one-dimensional convolutional neural network. So it's a deep neural network approach once again. So generally when we used SVM, or when we use SVM, that is a conventional classifier, or even when we have gone for deep neural network approach where we have used stacked autoencoder, we have provided certain features. But in feature engineering, it is said that feature extraction and selection of the relevant feature, it becomes a very challenging task. We that's why researcher has moved to these deep neural network approaches, where they have gone for convolutional neural network, or RNN, and different kinds of networks which do not require any future extraction and separation, and its selection. Rather, it will learn by itself. So the most or the major advantages of this convolutional neural networks, which is a deep neural or a deep learning approach, is that it eliminates the need of feature extraction and selection, which is a very cumbersome task in feature engineering. So this was the major advantage, that uh, that that 1D CNN, it has removed, it has eliminated the need of feature extraction and selection. So here directly we have provided the data to the convolutional neural network. So basically the segmented region of S1 and S2 with data length 18,190 were fed to the input layer of the network. So when we talk of convolutional neural network, so it has certain layers. So directly input was provided, 1D signal was provided. Actually, when we talk of phonocardiogram signal, speech signal, or electroencephalogram signal, these all are 1D signals here. So we have directly given the input here, and then in the first, it does the convolution. So it has some strides, and with the input, it does convolution as a convolution. Uh, but the dimension of the convolution will be very high. That's why there is a stage called max pulling. So max pulling, basically it reduces the dimension of the size. It takes only the relevant points so that the dimension reduces, and this again it is repeated to several times depending on the network's optimization. So again, convolution followed by max pooling. And when convolution and max pooling is done, basically the network does the work of a feature extraction by itself. We need not provide features as we did in our previous cases, like we have extracted spectral feature or analytical feature, or different combinatory features, which was the combination of skewness, kurtosis, and those features which have been much successful in speech recognition. So here no need to give any features, but it will try to learn from the signal directly, and then once, so after max pooling, it is fed to the classification part of the convolutional neural network. And we have tuned this, and we find that feature extraction is accompanied by convolving the input signal with the kernel size of 256. So actually there is a relationship between, like, the length of data and the kernel size, but we have to vary this kernel size, and we have to tune the network so that it gives the good performance. So first the convolution is done, and then it is followed by the downsampling of feature map through max pooling layers. And for the classification part, we have used multi-layer perceptron as an output layer, which comprises of two hidden layers with 220 neurons to achieve the maximum efficiency. So we have to tune this, and we found that the overall mean accuracy was 99.80 and 100% for online and experimental data respectively. So it is a superior method as compared to the previous methods. We saw two methods earlier. So one was based on the spectral and analytical feature, and the second was based on the combinatory feature followed by the stacked autoencoder. And this is the third method for recognition of S1 and S2, which uses 1D CNN. And the most advantage, or the better part of this is that it doesn't need, rather it eliminates the need of feature extraction and selection, and it outperforms the conventional methods. And then later on, mm, the 1D CNN, which was employed, or which was proposed, then we have that 1D CNN model. It was actually trained in Python, but we tried to dump that code in the Raspberry Pi 3B, and in the real time also, we tried to dump that into Raspberry Pi hardware. So this figure, so this is the work we tried to develop a hardware model of this. So here we found that here the recognition accuracy decreases. The reason of it decreases, it is not 100%, but we tested for, say, 10 number of heart sounds, S1. Then out of 10, it correctly detects 8 heart sounds, 8 heart, 8 S1 correctly. So there was a slight deterioration in the recognition rate as compared to what we have done in the Python, or in the software, on the software level. The reason is that here we have limited memory in the Raspberry Pi. That's why we decimated the signals, and we tried to reduce the size. We tried to reduce the kernel size also we reduced. Then we we decimated the signal also. As a result, we tried to lower down the memory in order to accommodate the things in the Raspberry Pi. That's why there was certain drawback, and then it was like real time also. That's why we need uh, so that's why more good training, or we have to use a hardware which have a some more memory. So still there are some scope for the improvement in this work. So it was based on some hardware things. So this I have already discussed that actually, mm, we have discussed several. So this 1D CNN, the proposed 1D CNN, it achieves higher classification accuracy as compared to staked autoencoder, which uses combinatory features and other conventional classifiers. And it eliminates the need of handcrafted feature extraction and selection. That's why this 1D CNN is suggested to be a better approach for recognition of fundamental heart sounds S1 and S2. Then the next work is detection of third heart sound. But before that, we have to separate heart and lung sounds from the breathing signal. That's why let us have a quick look on the technique which can be used to separate heart and lung sounds from the breathing sound. So now the first is that why there is a need to separate heart and lung sounds from the breathing sound. So previously also we discussed that whenever physician or cardiologist they do auscultation, it refers to hearing of heart sounds using stethoscope. So you might have seen that physicians or cardiologists they put the diaphragm of the elect- electros- electrostho- electrostethoscope to the right area of the chest, and they try to listen to that heart sounds in order to detect any abnormalities. But while listening to the heart sounds using stethoscope, which is also called auscultation process, so while listening to heart sound, lung sounds also mm, appears. They listen to lung sounds also, and while listening to lung sounds in order to detect some respiratory diseases, they also hear heart sounds. So there is a interference of these heart and lung sounds, and these interference cannot be removed using directly by direct application of low pass filter or high pass filter. It cannot be it's not possible, because some of the portion of heart and lung sounds have the same frequency components. It means there is a spectral overlapping between heart and lung sounds. So we cannot directly use low pass and high pass filters. That's why we have to go for some non-linear decomposition techniques like empirical mode decomposition or ensemble empirical mode decomposition or its higher versions. So in this work, we have hmm, we have proposed a method which can separate heart and lung sounds from the mixed signal or from breathing signal using a non-linear decomposition technique that is called variational mode decomposition. So here we are going to discuss how to separate heart and lung sounds using variational mode decomposition. And this variational mode decomposition, it's not that it can be applied to biomedical signals also, but in one of the research article, I found that this variational mode decomposition has been also used to to detect or to separate the background noise which is coming in one of the river in the river where people were sitting on the boat. So the reason is that when somebody is on the boat, then when they speak something, there may be some noise which is arising because of the motor of the boat. So the noise arising from the motor of the boat and the sound of the persons will be will there will be interferences. So there also we can apply these kinds of techniques which can separate these two signals. So basically it's a separation problem. So here our so this is this in this figure, actually it's the flow diagram of proposed method for heart and lung sound separation. So how it is done with the help of VMD. Let us see this. So here we have a mixed signal. Mixed signal means we have a breathing signal, and and we did so one is our breathing signal, but that will be for our recorded signal. But in order to get one another kind of breathing signal is that we have taken only heart sound signal and only lung sound signals, and we combined these two signals. So we have mixed it in the ratio of 1:1. One can mix it in the ratio of say say lambda hs plus 1 minus lambda ls, and we can vary the value of lambda as say zero point 0.1 zero point 0.2 till zero point 0.5 zero point 0.9 like this. So but we have considered the ratio as 1 and 1. So we have combined purely heart sound signal with the purely lung sound signal. So combined signal we have given here, and then we pre-processed it. Pre-processed means we use a uh, at the first we used only the low pass filter of higher cutoff frequency, say 800 hertz, and this pre-processed signal is fed to variational mode decomposition signal, variational mode decomposition, which decomposes that signal into 7 number of modes. So this 7 is actually why to decompose this signal into only 7 modes. So actually it's a user specific. So there is a reason that subsequently it will be discussed. So it decomposed the complex pre-processed signal or the breathing signal or a mixed signal into 7 modes, and then we combined 3 slowest modes, and this combination resulted in separated heart sound, and the rest of 4 higher modes we combined, and that were our lung sounds. It means that the complex signal was decomposed into 7 modes, and the 3 slower modes were combined to get the reconstructed heart sounds, and remaining higher modes were combined to get the uh, separated reconstructed lung sounds, and these separated heart sounds were very close to the original pure heart sounds, and these reconstructed or separated lung sounds from the complex signal was very close to uh, that of the that of the pure lung sounds which we have combined earlier. So here, like first we have used mixed signals. So heart sounds and lung sound signals were obtained from various databases. They were combined in the time domain to generate mixed signals. So we generated 94 mixed signals that were equivalent to 94 breathing signals. And this was for online, and we have done this for our experimental signal also, where we used where 8 subjects were volunteered to give their breathing signals. So here we find that the first is our actually this is the demonstration of various steps of our proposed schemes for heart sound and lung sound separation. So here this is our original signal here, uh, where uh, where both the signals are present here. We can see here it is S1, S2, this is S1, S2, and then you find here in between this area, from this point to this point, it's the lung sound signal is also overlapped here. Similarly, this is S1, this is S2, but whole region is overlapped by the lung sound signal. So when this signal is decomposed, this figure A, sub-figure A, is decomposed into 7 modes, and 3 slow modes or 3 low frequency components were added. 3 modes were added, and it resulted in heart sounds. And the remaining uh, 4 modes of higher frequency, this resulted in lung sound. So we can find that from this combined signal, from this breathing signal, we can separate heart sounds and lung sounds. So now these separated heart sounds, it can be fed for, or this can be considered for separate analysis for cardiac abnormalities, and these lung sounds can be independently analyzed for respiratory diseases. And then we tried to compare this variational mode decomposition with its previous nonlinear decomposition techniques like empirical mode decomposition technique, ensemble empirical mode decomposition techniques. Then we have empirical complete ensemble empirical mode decomposition, and complete ensemble empirical mode decomposition with the residual and adaptive noise. And we used this VMD method, and we found that this VMD method gives lowest mean square error and standard deviation as compared to other nonlinear decomposition techniques. And it's true for the online as well as recorded data also. So we found that variational mode decomposition is more effective as compared to its previous nonlinear decomposition techniques like empirical mode decomposition and its higher variants in order to separate heart and lung sound signals. And then as we know that these are like subjective, like this is whatever the result we obtained here, that was basically numerical data. It was a numerical result, but whether this error or this segmented or the reconstructed or separated heart and lung sounds which have been the result of application of variational mode decomposition is really meaningful, uh, does it really contains clinical information? For that we did kappa score measurement. So basically when like we did professional validation also, like we tried to we requested 2 physicians and randomly we have made them listen to these separated heart sounds without telling whether it's a lung sound and heart sound. So the question was like, the question asked was, are lung sounds audible and of clinical importance? And then we tried to give them 50 sounds. So we have 2 medical here. So out of randomly 50 separated lung sounds, they told that both the physicians were agreed that 47 were really it's a lung sound, and it contains some of the clinical importance in it. Then there was a mismatch in one of the signal. One physician told that yes, it's a lung sound and it contains and it has some medical importance, whereas another physician, he was disagreed. And for one signal, out of the 50 randomly separated signal, both were in opinion that it is not a lung sound, and it doesn't carry any information. So still, out of 50, 47 signals were correctly separated. So we have and this kappa static, when we talk of kappa statistic, so it is generally thought to be more robust measure than simple percent agreement calculation, since kappa considers the possibility of agreement occurring by chance. Here means like two persons will be there, or even more than two persons, and then it measures the agreement as well as disagreement also. That's why it's more effective. So there is a 96% of agreement on the presence of audible clear lung sounds having clinical information. so so this variational mode decomposition, it proves to be very successful in separating heart and lung sounds from the breathing signal, or from the mixed signal. And this is actually we try to, so whenever we want to separate these heart and lung sound signals, so how to record those signals? So we try to design a mini printed circuit board for data recording. So this is the layout of a PCB signal, and PCB printed circuit board, and it was designed using ORCID capture version 16.3. So it's a very simple circuit. Here actually it uses IC like AD620 and TL084. So basically it uses a low pass filter followed by a differential amplifier, because it's a biomedical signal, so we have to go for uh, instrumentation amplifier, uh, differential amplifier. So here signal, this is our microphone. So we can see here that actually here we have this microphone of, actually it is the portion of a stethoscope. So here in that stethoscope we put a microphone so that it can capture the heart sounds. Then it is fed to this PCB, this mini PCB, and this is the battery which is power supply from this battery which is given to PCB. And this, from this PCB, the output is connected on the CRO to see whether it is able to capture or record the heart sounds or not. The same can be fed to the laptop also, or to the desktop. So here actually what is happening here, the microphone of the diaphragm, and then here simply there is a low pass filter followed by amplifier. So here we have applied this in this PCB, and we have recorded, and we found that uh, physician says that the recorded signal which is by our design PCB is very close to that of the electronic stethoscope signal, and the cost of electronic stethoscope is much higher as compared to the setup which we tried to implement using a hardware. So this is also a very good area where hardware implementation can be done. Then not only the recording part, but even the detection part can also be done in the hardware. So that will be a very good project indeed. So we have designed a mini circuit, a mini printed circuit board for data recording, and it was close to that of the electronic stethoscope. So it was a cost-effective uh, design, you can say, for data recording. But still, it needs improvement. It is not as robust to that of the electronic stethoscope. So here we saw how to separate heart and lung sounds using variational mode decomposition. Now I have around 10 minutes in hand. So let me just quickly discuss my work on detection of third heart sounds using variational mode decomposition. So like whenever we go for detection of third heart sounds, it is necessary that one should go for segmentation of first and second heart sound first. Then as this third hertz sound is of very low frequency and low amplitude, so it's always important to separate heart sounds from the combined signal, from the breathing signal. That's why we have seen the separation of heart and lung sounds. And then when we have only heart sounds, then we can go for detection of third heart sound. And detection of third heart sound is a challenging task as compared to the detection of first and second heart sounds, because third heart sound is of very low frequency and low amplitude in nature. So this is the proposed method. This is the proposed method for detection of third heart sounds. So either we have a combined heart sounds, the breathing signal, or we may have a phonocardiogram signal containing S3. And we know that S3 is the third heart sound. This may be normal in case of a children, juveniles, or some athletes, but the presence of third heart sound S3, it indicates cardiac abnormalities for elderly person. So we do pre-processing where we do normalization of a signal, decimation if required, and then using a low pass filter of cutoff frequency 400 Hz, because most of the energies of the signals of these heart components lie within 400 Hz. So we can you go for a low pass filter of 400 Hz as a cutoff frequency. Then we decompose that signal using variational mode decomposition techniques. So signals will be decomposed. So here also again we decompose that into 7 modes, as we discussed previously in the separation of heart and lung sounds, because here we have a combined signal, or even if we have a PCC signal with S3, so we decompose that into 7 modes, and then 3 slow modes are clapped together, are added to give us only the pure heart sound signal. And then this heart sound signal containing S3, we represent that using time frequency representation technique. And here we have used smoothed pseudo Wegener value distribution technique, as it has few advantages over short time Fourier transform, or S transform, or even Wegener value distribution. So it has certain advantages. That's why we have tried to represent this one dimensional heart sound signal in the time frequency representation, where we have both the information there, time as well as frequency. So it becomes a 2D signal here. And then in that 2D signal, where one is say time and another is frequency, we try to add the values of that matrix column wise, and then we plotted that. So that plot gave us the value of S1, S2, and S3, and with the help of timing information we can easily detect this S3. So here when we talk of S3 signals, so basically S3, it is recognized as identification of heart failure. It originates from the left or right ventricles or their walls, and it occurs at around 1000 to 150 millisecond just after S2. And it has a very low frequency of approximately 30 to 90 hertz, and it continues for almost 70 millisecond. It may vary, like it may be maybe 85 millisecond. It can last for maximum of 85 second, or it may it last for only 55 seconds also. So so here we can see the results. Like first we have two cases here. One is for noisy cases and another is for noiseless cases. So this is a pre-processed cardiac signal containing S3. Then we have decomposed this into 7 modes, and we combined only the 3 modes. So this is the pre-processed heart signals here, this one. Then with the help of SPWVD, we have represented this signal in the time and frequency domain. And then column wise we have added this, and here energy is more, so we have more plot here. Then this signal is S1, this is S2, and this is S3. So this S3, if we see the amplitude of S3 to that of the maximum value of S1, then its ratio can be found. And we have found that uh, very with very low, means even if its value of S3 is low, But still, this SPWVD, it helps us to detect S3 signal. So it detects S3 here. So for noisy as well as noiseless cases, this technique is able to detect S3 components. And we have compared this with different time frequency representation techniques, and we find that this VMD, so even the value or the relative amplitude of S1 is say only the 14% as compared to highest peak, then also VMD is able to detect. Whereas other techniques, they require that S3's amplitude should be higher as compared to 14%, then only they are able to detect. But even if the value of S3 is low, also VMD is able to detect. So it has certain advantages. And for noisy cases also, VMD performs very well. So this shows here also, like for noisy cases we can find that that like if we use, like this is the noisy cases here, we see. So different techniques we have used, like the first is our noisy signal. Then when we use STFT, short time Fourier transform, then it is unable to detect S3. Here also, like then then here S3 is a bit clear here. But in case of VMD, the last one, VMD based normalization, so here S3 is more clear. So VMD is effective in noisy conditions also. And out of 40 signals, in case of minus 10 dB, where the noise is very high, VMD is able to detect 10 S3 out of 40 S3, whereas HVD, that is Hilbert variational decomposition, it detects only one. Whereas short time Fourier transform, S transform, and Hilbert Huang transform, these are unable to detect S3, as it cannot be it is unable to correctly recognize in the noisy cases. So I can understand we have low time now, almost it's 4. So basically contribution, when we talk of the contribution of this work, then it lies in introducing a method for detection of third hertz sound S3 using variational mode decomposition and SPWD techniques. And average lower limit of normalized amplitude is just 14%, but in the stata part it's 16%. So even if the amplitude is low also, this technique is able to detect S3 correctly. So with this, let me just go to, and these things sometime we will discuss. These are the different areas where we can discuss. So and this work has led to some publications. And at the end, I would like to thank you for your attention and valuable time. I would like to convey my gratitude and greatly appreciate the organizing committee members and coordinator of this program, especially Dr. Swanirbar sir, head of the Department Information Technology, Tripura University, for giving me this opportunity to present my research work. I really feel privileged to share a few words with you. So thank you, and thank you very much. And questions are welcome from your end.
Thank you, Madhusudhan sir. It is a joint effort. The electronics department, uh, actually, we are having 2 faculty members of electronics, along with 5 of us from IT, who are actually involved in this small program with small group of people. We are working on it. Thank you very much. And participants, do you have any questions? Because I see very less participants here. So those who understand mainly are here, I guess. And moreover, irrespective of CS, EC, IT, deep learning, and machine learning, what sir has discussed is used by everybody now. So if you have any questions, sir is here. The floor is open.
Hello, thank you, sir, for your that valuable presentation.
Yeah, thank you.
Yeah,
Welcome.
one of
He
my
is the
question is
head of
that
electronics department.
Okay. Oh,
okay, sir. One question is there. what are the hardware requirements? What are involved in your total experiments?
Yeah. Actually, sir, actually, when we talk of hardware requirement, the first requirement starts from the recording of a signal. Like when we are not using online database, which are available publicly, in that case, the first step is to have the stethoscope. So in most of the work I have seen, they are using electronic stethoscope, and that is quite costly. So the range is around 60,000, 70,000. So that is the electronic stethoscope. So it gives a facility to record the signal, and directly by with the help of physicians, you can directly record it on your laptop, your PC, even on CRO. So one hardware requirement is this stethoscope. So one can go for low cost designing of cost effective designing of this stethoscope using using mini circuit board, where you can just try to replicate the things which are available in the hardware of an electronic stethoscope. Secondly, when whatever we do on the software, some classifier, pre-processing, all these things, so that can be dumped into a hardware. So for there you can go for Raspberry Pi models, or some embedded design, embedded method. So mainly when we talk of the hardware requirements, so the first starts with the recording, followed by the hardware components like Raspberry Pi or special embedded systems that can be which can be dumped into those things. And nowadays most of the people are preferring to record the signal using Bluetooth, where there will be no physical contact. And in mobiles also these days you will find, and in mobile also data recording can be done, and process, and it will process also, and it will tell whether heartbeats is fine or not. Even nowadays, there is a trend in wearable biomedical devices. So wearable, we can wear that in our body parts. So these are the trends available or seen in the hardware part of the phonocardiogram signal analysis.
Okay, thank you, sir.
Welcome, sir.